is wet compression cycle, we would have to calculate the dryness fraction X1 for calculating the H1, so that we can calculate the COP as H1 minus H3 divided by H2 minus H1. Now, how to get the X1? By equating the entropies. S1 is S2. What is S1? SF plus X1 into SFG at evaporating temperature of T1, that is minus 20 degrees centigrade, is equal to what is S2? S2 is SG at evaporating temperature, at condensing temperature of T2 is equal to 40 degrees centigrade. Implies from the given data, the SF at minus 20 is 0.07 plus X1 into what is SFG? SFG is equal to SG minus SF. SG is given as 0.7366 minus 0.07, that is SFG, that is equal to SG at 40 degrees centigrade is 0.67, from which the dryness fraction of refrigerant at inlet to compressor can be calculated. Once after getting the dryness fraction, I can get the enthalpy at inlet to the compressor as HF plus X1 into HFG at minus 20 degrees centigrade. This is minus 20 degrees centigrade. This is equal to what is HF 20 plus X1 is already obtained there into HFG is HG minus HF 20 plus X1 into what is HG at minus 20, that is 180 minus HF, that is 20, so many kilojoule per kg. After having obtained H1, COP of cycle is equal to H1 minus H4 divided by H2 minus H1, that is refrigeration effect divided by work done. But H4 is H3, since 3 to 4 is throttling. Therefore, COP is equal to H1 minus H3 divided by H2 minus H1. We already got H1. What is H3? H3 is HF at minus 20. That is 20 divided by H2 is, what is H2? H2 is HG. HG at plus 40 degrees centigrade. That is given as 200 minus H1. H1 is already obtained just above as such. Therefore, substitute there and get the COP, coefficient of performance. And next question is mass flow rate of the refrigerant is given as 0.025 kg per second. Then refrigeration effect per second is equal to mass flow rate of the refrigerant into refrigeration effect in kilojoule per kg. That is mass flow rate of the refrigerant into H1 minus H4 or mass flow rate of the refrigerant into H1 minus H3. That is 0.025 into H1 minus what is H3? H3 is given from the table, that is 40 degrees centigrade, H of that is 80. So many kilowatts. There is a small correction in the COP formula. We had taken H3 as 20. H3 is not 20 in the COP formula. H3 is 80. Please correct that. Please correct that. The COP H3 we had taken as the COP substitution. H3 we had written as 20. It is not 20. In fact, H3 is HF. This is HF at 40, which is given as 80. So we got the refrigeration effect also in kilowatts. Now let's solve a problem given in GATE 2004 on the vapor compression refrigeration cycle, which is given as, the problem is given like this: a R12 refrigerant reciprocating compressor operates between the condensing temperature of -30° centigrade and evaporator temperature of -20° centigrade. The clearance volume ratio of compressor is 0.03. Specific heat ratio of the vapor is 1.15, and the specific volume at the suction is 0.1089 meter cube per kg. Other properties at various states are given in the figure. To realize 2 tons of refrigeration, the actual volume displacement rate considering the effect of clearance is, the given figure along with the problem is pH chart, pressure is in bar, -20° centigrade and 30° centigrade are the saturation temperatures. Here the pressure is 7.45 bar, and here the pressure is 1.50 bar. 3, 4, 1, 2. This is the cycle given along with the problem. Enthalpy here is 65. The H1 is given as 176. H2 is given as 207. The compressor displacement rate, the answers were given as optionals. That is A, 6.35 into minus 3 meter cube per second. B, 63.5 into 10 power minus 3 meter cube per second. C, 635 into 10 power minus 3 meter cube per second. D, 4.88 into 10 power minus 3 meter cube per second. The solution to this problem could be given as, because the compressor displacement rate, actual compressor volume displacement rate is to be calculated. First of all, let us obtain the volumetric efficiency of the compressor. The volumetric efficiency of reciprocating compressor is equal to one plus C minus C P delivery by P suction whole to the power of 1 by N, where N here is specific heat ratio of the refrigerant, which is given as 1.15. C is clearance ratio, that is clearance volume by stroke volume. This is given as 0.03. PD is given as delivery pressure is 7.45 bar. P suction is 1.50 bar. Because that is evaporator pressure is 1.5, which is the suction pressure into the compressor. This is compressor compression 1 to 2. Delivery pressure P2 is given as 7.45 bar. Therefore, volumetric efficiency of compressor is equal to 1 plus 0.03 minus 0.03, 7.45 divided by whole to the power of 1 by 1.5. We will obtain volumetric efficiency, which is in the range of 70 or 75%. Now he has asked the actual volume displacement rate. He has asked. Now V1, specific volume of refrigerant at inlet to compressor is 0.1089 meter cube per kg. That is the specific volume of the refrigerant at the inlet to the compressor. The refrigeration effect RE from the cycle, it is H1 minus H4 kilojoule per kg is equal to H1 minus H3 kilojoule per kg. That is 175 minus 65 kilojoule per kg. This is RE. It is given tonnage capacity as 2 tons, which is equal to mass flow rate of the refrigerant into RE divided by 210, so many tons, from which mass flow rate of the refrigerant in kg per minute is equal to 210 into 2 divided by RE. RE is 175 minus 65. We got mass flow rate in kg per minute. Mass flow rate of the refrigerant through the compressor implies volume flow rate of refrigerant through compressor is equal to mass flow rate of the refrigerant into V1, specific volume at inlet. That is 210 into 2 divided by 175 minus 65 into V1, specific volume is given as 0.1089 meter cube per minute. So this volume flow rate must be equal to the V stroke into volumetric efficiency into N, implies compressor displacement rate, that is equal to pi by 4 d square L into N. The volume displaced by the piston per minute is equal to volume flow rate of refrigerant per minute divided by volumetric efficiency, that is 210 into 2 divided by 175 minus 65 to 0.1089 divided by volumetric efficiency is already earlier obtained. So that gives the compressor displacement rate in meter cube per minute. Because since the answer is given in second, compressor displacement rate in meter cube per second is equal to, we have to divide the above thing with 60. So many meter cube per second. The problem is given in GATE 2002 rice making plant working on vapor compression refrigeration system. The problem is given like this: an ice making plant working on R12 is having an evaporator saturation temperature of minus 25 degrees centigrade and the condenser saturation temperature of 35 degrees centigrade. The vapor is leaving the compressor at 65 degrees centigrade. Following table shows the properties of refrigerant. The table is given like this. First column is saturation temperature. Second column is saturation pressure in kilopascal. Then we have saturation enthalpy in kilojoule per kg for liquid, for vapor, for minus 25 degrees centigrade it is 123.7 kilopascal saturation pressure. Saturation enthalpy is 13.3 for liquid, 176.5 for vapor. 35 degrees centigrade for saturation temperature. The pressure is 850.0 kilopascal. For liquid it is 69.6 saturation enthalpy. For vapor it is 201.5 kilojoule per kg. Enthalpy of superheated refrigerant vapor at 850 kilopascal and 65 degrees centigrade is 225.5 kilojoule per kg. This is how the problem is given. The things that are to be calculated in the problem are: number 1, calculate A, COP, B, tonnage capacity of the plant in kilowatts, C, what is the power consumption by the compressor in kilowatts. Now let's draw the cycle based on the given data. The refrigerant is R12 or Freon 12 or CCl2F2 dichloro-difluoromethane. The solution to this could be given as temperature entropy diagram. We shall indicate assuming a simple dry saturated cycle 1, 2 dash 2, 2 dash 3, 4. This is compression. He has given this temperature as 65 degrees centigrade, and this temperature, condensing temperature, is 35 degrees centigrade. Evaporating temperature is minus 25 degrees centigrade. Now let us calculate the refrigeration effect. RE is equal to H1 minus H4 kilojoule per kg. Since H4 is H3, H1 minus H3 kilojoule per kg RE. H1 is Hg at minus 25 degrees centigrade. This is given as 176.5 dry saturated vapor enthalpy. H3 is Hf at 35 degrees centigrade condensing saturation temperature, that is given as 69.6 kilojoule per kg. Having obtained refrigeration effect, that is H1 minus H3 kilojoule per kg, let us calculate work done per kg of refrigerant is H2 minus H1 kilojoule per kg. H2 is given in the problem as H soup at 850 kilopascal, that is condenser pressure, and 65 degrees centigrade superheat temperature. It is given as 225.5 kilojoule per kg. Therefore, COP of the system, VCR system, is equal to H1 minus H3 divided by H2 minus H1. We can obtain the COP. Now, coming to the mass flow rate of the refrigerant, the tonnage capacity of system is given as 5 kilowatts in the problem. It is given. Therefore, tonnage capacity is equal to mass flow rate of the refrigerant in kg per second into refrigeration effect in kilojoule per kg. Therefore, mass flow rate of the refrigerant in kg per second is equal to 5 kilowatts divided by H1 minus H3 kilojoule per kg. That should be the resultant answer is in kg per second. This is one of the answers for in the unknowns, that is mass flow rate of the refrigerant. Now let us calculate the power input to the compressor. Power input to the compressor is equal to mass flow rate of the refrigerant into work done per kg. Mass flow rate of the refrigerant in kg per second into H2 minus H1 kilojoule per kg. The resultant power unit will be kilowatts. That is answer. It was given tonnage capacity as 5 kilowatts in the problem. Now let's do a problem given in GATE 1997. Problem in GATE 1997. It's given on VCR system. The problem is given like this. In a standard vapor compression, refrigeration cycle, operating between an evaporator temperature of minus 10 degrees centigrade and a condenser temperature of 40 degrees centigrade, the enthalpy of the refrigerant Freon 12 at the end of compression is 220 kilojoule per kg. Show the diagram on TS plane and calculate A, the COP of the cycle, B, the refrigerating capacity and the compressor power, assuming a refrigerant flow rate of 1 kg per minute. The extract of Freon 12 property table is given as, along with the problem, at a saturation temperature is T degrees centigrade, first column, P in megapascal saturation pressure, second column, HF in kilojoule per kg, that is a saturated liquid enthalpy, and Hg in kilojoule per kg, that is dry saturated vapor enthalpy. At minus 10 degrees centigrade, P is 0.2191 megapascal, HF is 26.85 kilojoule per kg, Hg is 183.1 kilojoule per kg. At 40 degrees centigrade, P is 0.9607, HF is 74.53, Hg is 203.1 kilojoule per kg. The solution to this problem is given as, first of all, let us indicate the cycle on TS plane, temperature entropy diagram, evaporation, compression, cooling, condensation, and then expansion. The simple dry saturated VCR cycle. He has given the enthalpy of the refrigerant at the end of the compression. It's given that H2 is 220 kilojoule per kg. H1 is Hg at evaporating temperature of minus 10 degrees centigrade, that is 203.1 kilojoule per kg from the table. H3 is HF at plus 40 degrees centigrade, the saturation temperature corresponding to condenser pressure, it is 74.53 kilojoule per kg. Therefore, immediately I can calculate COP of cycle is equal to refrigeration effect divided by work done, that is H1 minus H4 divided by H2 minus H1, which can be written as H1 minus H3 divided by H2 minus H1, that is H1 is given as 203.1 I'm sorry, I had taken wrongly for H1. Minus 10 degrees centigrade, Hg is 183.1. That please indicate that is H1 is Hg at minus 10. that is given as 183.1. 183.1 minus 74.53 divided by 220, that is H2, minus 183.1. This gives the COP. Please note that Hg at minus 10 degrees centigrade is 183.1. That is how we can obtain the COP of this cycle, which may be coming around 2 or 3. Now it is given in the problem the mass flow rate of refrigerant is equal to 1 kg per minute. Therefore, tonnage capacity or refrigeration capacity of plant is equal to mass flow rate of the refrigerant into RE divided by 210. This is 1 into H1 minus H3 divided by 210, so many tons. H1 we had already noted as 183.1 minus H3 is 74.53 divided by 210, so many tons of refrigeration. This is the refrigeration capacity of the plant. Now coming to the power required for compressor is equal to mass flow rate of the refrigerant into work done per kg in compressor, that is mass flow rate of the refrigerant in kg per second into H2 minus H1 kilojoule per kg. Kg gets cancelled, you get the resultant answer in kilowatts, that is 1 by 60 into 220, that is H2, enthalpy at the end of the compression, minus H1 is 183.1, so many kilowatts. This is the power required for the compressor. Answer. Now let's do a problem given in GATE 1996. The problem is given like this. In a simple vapor compression cycle, following are the properties of the refrigerant R12 at various points. The points are given like this. Compressor inlet H1 is given as 183.2 kilojoule per kg. V1 means specific volume, 0.0767 meter cube per kg. Compressor discharge H2 is equal to 222.6 kilojoule per kg. Specific volume at 2V2 is 0.0164 meter cube per kg. Condenser exit, that is H3, is 84.9 kilojoule per kg. V3 is 0.000083 meter cube per kg. The piston displacement volume is 1.5 liters per stroke. The volumetric efficiency of compressor is 80% and the speed of the compressor is 1600 rpm. Then calculate A. Refrigerating effect in kilowatts. B. Power rating of compressor in kilowatts. The solution to this problem can be given like this. First of all, let us draw the cycle on TS plane. One, two, three, four, the salient points of the cycle. This is a compressor inlet. This state is condenser exit. Therefore, first of all, let us calculate what is the refrigeration effect. That is equal to RE is H1 minus H4 kilojoule per kg, which is nothing but H1 minus H3 kilojoule per kg. Therefore, RE is equal to 183.2 minus 84.9 kilojoule per kg. Now, then to get the refrigeration capacity in kilowatts, we have to calculate the mass flow rate. Mass flow rate of refrigerant through compressor is equal to volume flow rate of refrigerant in meter cube per minute divided by specific volume at inlet to the compressor. V1 is specific volume of refrigerant at inlet to compressor in meter cube per kg, which is given there in the as 0.0767. But how to get the volume flow rate of refrigerant? Therefore, volume flow rate of refrigerant in meter cube per minute is equal to pi by 4 d square L into volumetric efficiency, that is the actual volume utilized per cycle, into number of cycles per minute, that is RPM n. Piston displacement is given as 1.5 liters into 10 power minus 3 so many meter cube. Volumetric efficiency is given as 0.8. RPM is given as 1600. This is the volume flow rate of the refrigerant in meter cube per minute. Pi by 4 d square L is the stroke volume, out of which the actual volume utilized for sucking the refrigerant is pi by 4 d square L into volumetric efficiency, that is per cycle. Per minute, that should be multiplied with n. Therefore, mass flow rate of refrigerant through compressor is equal to 1.5 into 10 power minus 3 into 0.8 into 1600 divided by specific volume at inlet of the compressor is so many kg per second. I'm sorry, kg per minute. Please correction, because volume flow rate is in kg per minute. Mass flow rate in kg per minute. That is the answer we got. Now the refrigerating capacity in kilowatts is equal to mass flow rate of the refrigerant in kg per second into refrigeration effect in kilojoule per kg, that is equal to 1.5 into 10 power minus 3 into 0.8. This is mass flow rate of the refrigerant in kg per minute, divide with 60 so that we get the m dot in kg per second. M dot is mass flow rate into refrigeration effect is 183.2 minus 84.9. This gives the refrigeration capacity in kilowatts. That is one of the answers. Now to get the power rating of compressor, that or compressor power, it is mass flow rate of the refrigerant in kg per second into work done per kg in kilojoule per kg. We already got mass flow rate of the refrigerant in kg per second earlier. Work done per kg is H2 minus H1. Mass flow rate of the refrigerant in kg per second, which we got earlier, H2 is given as the data compressor exit 222.6 minus compressor inlet is 183.2. This is the work done per kg in kilojoule per kg. You get the compressor power in kilowatts. Kg gets cancelled. Kilojoule per second is kilowatts. This is the another answer that is asked. Now let us discuss about desirable properties of refrigerants. First of all, what is a refrigerant? A refrigerant is an artificially made chemical substance. In fact, they are the derivatives of the methane and ethane. Hence, any refrigerant can be called as a, most of the commercially available refrigerants are halogenated hydrocarbons. They are derivatives of the methane and ethane. Most of the refrigerants, like Freon group refrigerants, for example. So what are the important desirable properties? If you look at, first property is the refrigerant should have high latent heat of vaporization. What for? To produce more refrigeration effect per kg of refrigerant. A refrigerant, if it has got more latent heat or more HFG at a given evaporator pressure, it can give us more RE. For example, ammonia. Ammonia is the one of the refrigerant which has got the highest latent heat of vaporization or HFG at a given evaporator pressure. Hence, it is preferred for large tonnage units. NH3 is the inorganic refrigerants which has got the highest latent heat of vaporization. Second, the refrigerant should have low specific volume to occupy lesser space required by the refrigeration unit. For the entire refrigeration unit to be compact or to be smaller in size, the refrigerant should have low specific volume in meter cube per kg, because the compressor size, the compressor RPM, and all these things are decided by the specific volume of the refrigerant at the inlet of the compressor. So as we had seen in the earlier problems also, the compressor size is in another way decided by the specific volume of the refrigerant at inlet to the compressor. So it should be lesser. Number 3, the critical pressure and critical temperature of refrigerant should be as high as possible, that is well above condensing pressure or temperature of refrigerant in the cycle, so that the power required by the compressor of cycle is lesser. If the critical pressure of the refrigerant is very high, that is well above the condensing pressure, the power required by the compressor will be lesser, and hence COP may be more. So if power is the criteria or if COP is the criteria, we should always choose a refrigerant which has got very high critical pressure and critical temperature. What is meant by critical pressure or critical temperature? Critical pressure is the pressure. I define critical pressure here in this context. Critical pressure is the pressure above which the vapor shall never condense into liquid, however low the temperature may be. if the pressure of the refrigerant is above its critical pressure, whatever the way you cool the refrigerant, whatever the cooling you provide for the refrigerant vapor, it would never condense into the liquid. Fourth point. The refrigerant, it is a physical property. The refrigerant should have low viscosity for easy flow. It should have high thermal conductivity K to have better heat transfer, better convection heat transfer coefficients in the evaporator and in the condenser. The refrigerant should have a good value of the thermal conductivity. It should be non-toxic. Even if it is leaked, it should not spoil the food commodity that has been stored inside the refrigerator. It should be non-corrosive. Or non-reactive. With metals used in evaporator and condenser. It should not react with the pipe material that are used in the evaporator and condenser. Particularly when ammonia is used as a refrigerant, because it might react with copper. Therefore, when ammonia is used as a refrigerant, the evaporator pipe and the condenser piping should not be made with the copper and its alloys like brass, bronze, etc. Cast steel may be employed. So aluminum could be used. Hence, because ammonia is not reactive with the cast steel. Now let us look at the another type of the refrigeration system, which is vapor absorption. Vapor absorption refrigeration system. This is also known as VAR system. In a VCR system, the type of energy input to the system is mechanical shaft work or shaft power, which is considered as high grade energy or costlier mode of energy. But in VAR system, we give energy input in the form of low grade energy, that is heat energy. Heat energy is considered to be a low grade energy or cheaply available energy. The availability of heat energy is abundant, but whereas the availability of the mechanical shaft power is difficult.